Okay. Now, last time we covered nuclear fission, and as you know, I mean, it's changed the world forever. You can't reverse it because uh, whether you're talking about, even if you talk about nuclear power reactors can be substituted with some other form of energy, that's fine. But the destructive use of nuclear power is not going to go away. I mean, that is a threat which will be there forever. That's not going to go away. Okay. Now, what is very interesting is more or less around the same time. You saw that finally, it was around 1939 that Hahn was able to figure out really the both components of the product, which is barium and krypton. Okay, and it's very interesting that more or less around the same time, 1939 or thereabouts, actually the beginning of solar photovoltaic power, the most important significant work that was done, actually happened. And today, I mean, we bang so much and say nuclear, solar, but we should really understand where it came from. So that's what I'll be doing in today's lecture. Probably you have seen this before, but it's interesting that this talks about top 30 innovations of last 50 years, and photovoltaic solar energy figures in that. Okay, but actually the primary invention really took place, as I told you, in the late 30s. But the patent was granted around 41. So we are really not talking about last 30 years. Maybe what these people talk about, when they talk about innovations, is that when they really become more commonplace, and the prices also crash, and these things get introduced in the market. Not that the fundamental invention occurred in the last 30 years, but probably yes, it is true that big scale, large scale commercialization has happened in the last 30 years or so, or last 40 years. And later on, we will be also covering two others, which are in this. One is the light emitting diodes. The other is fiber optics. These are extremely important. Now, let us try and find out, as I've been doing in all the various inventions. I like to give a background of how did it all happen. I don't like to just tell you this is the invention. That's not really the way things happen. And what you, as potential brilliant scientists, what you and engineers, what you must look at always is the early stage of conception, not when everything is known already and then you jump into the fray. So a significant part of this course is meant to make you think along those lines. How did it all begin? Okay, now if you look at even the solar photovoltaics, uh, actually you can, after all, what is photovoltaics? I mean, there is a illumination by light, of some object surface, and then there is a response. Yeah? And in photovoltaics, the response is electrical power. But there could be other kinds of responses of an incident radiation. Uh, but the person who really found out photoelectric effect for the first time, a lot of people think it's Einstein. It's not Einstein. It was in 1839 that the father of Henry Becquerel, the father of radioactivity, okay, he is the one who actually found that, when some metals are struck by light, that it generates a current. What a amazing family, almost like Curie family. to have father and son, making such spectacular inventions is just mind-boggling. That was 1839, and almost about more than 30 years later, you know, this person was able to apply that observation of Becquerel, okay, and he's the one who actually created the first what we'll call a photocopying machine, okay, and what he found is that of course you could use various kinds of metals which Becquerel had shown, but he found that selenium, you know, was an amazing element if you apply an electric field, okay, very high electric potential, and the surface gets charged. But what was very interesting is that the like something like Langmuir had found that the surface charge remains very localized. It does not diffuse laterally. So immediately people thought that there's a potential for an interesting application because of the lack of lateral movement of the charge, and and later on, what they did was that if I take a paper with the writing, okay, and let's say it's white and black is the writing, okay, wherever light strikes, on that paper, okay, the white part of the paper, I mean, the light gets reflected, okay, and from the black part, it gets absorbed, okay, and that reflected light, okay, from that was effectively falling on this charged selenium drum, and because of a photoconductive nature of the drum, okay, it was ejecting electrons, okay, and that electron was going and neutralizing the charge on the charged selenium drum. Wherever it was black, the charge was not getting neutralized. Everywhere else, it was getting neutralized. And so because of that, what happened is that then they introduced a resin, a charged resin, which could go and sit on the unneutralized parts of the selenium drum, where the charge was still there, and so because of that, it became an exact image of the paper, which you're trying to photocopy, okay? And then the paper really goes around, and the toner resin then gets transferred from the drum, to the paper, and because it's quite hot, the polymer in the resin gets fused, and the image gets fixed. So that was probably the most important application of photoelectric effect, and even today, photocopying is something so important. It was, of course, Einstein who later on was able to really explain the effect. Today we take it for granted, but in those days there was very little known. The quantum concept was just emerging, okay? And it was Einstein who, for the first time, figured out that the kinetic energy of the ejected electron is really equal to h nu, where f is the frequency of the light, and phi is the work function, okay, of the metal. So that's the minimum energy that you would require to kick off the electron, And he was the one who showed that it's not an intensity effect, it's a effect of the frequency, okay. And then he was able to figure this equation out, and this is why he got the Nobel Prize. And what was very significant was that this is the time when light got quantized. Okay? So that was very important, that he was able to introduce H, and later on Robert Millikan actually verified that this H and the H which was obtained by Planck, from his study of black body radiation was the same age. Okay, so Robert Millikan actually verified Einstein's equation and also proved, that the two H's are the same. It's also very interesting that when Planck actually wrote down his Planck's equation, of black body radiation, and he found that this H was fitting in well, and he was able to simulate the black body radiation. But it is not as if Planck had a very good idea about quantum. He used it as a constant, which worked well. But it was Einstein who really then was able to associate the quantum with photons. And so I mean, between Planck and Einstein, they really laid the foundation, of quantum effect. Uh, but much later than that, after 1916, 1940, was this person we will be talking about, Russel Ohl, worked in Bell Labs. Okay? And Russel Ohl was the person who is credited with the invention of the photovoltaic solar cell as we know it today, the silicon solar cell, which even today, is the mainstay of all solar power. He is the one. And what is remarkable is that in the process, of whatever work he was doing, he also was able to explain, whatever was happening through the incorporation of a PN junction. So Russel Ohl is also credited for inventing the concept of the PN junction, which then gave birth to the transistor. So it's amazing that the PN junction and the solar cell are covered in the same patent, which I will describe to you, okay, and which lays the foundation for all of whatever communication today we have. All of this is really based on the PN junction. Okay, so I hope you can understand how important it is. And believe it or not, he didn't get the Nobel Prize, and it went to others. I mean, it seems very, very cruel, that they did not give it to him. Okay? It was these people subsequently around 54, almost about 15 years or 10 years. I mean, by the time they did their work, 10 years after Russel Ohl's work, that these people were able to make the photovoltaic device practical. When we say practical, it is not as practical perhaps as today's photovoltaic cells, but not bad. It was a very, very significant milestone, because they achieved something like a 6% efficiency of light to electricity conversion. Okay? And that's what gave birth to, again, all these satellite applications, because that was the only way in which these satellites could be powered. So, I mean, what a revolutionary thing happened. I hope you can imagine. And there was a feeling in 1954, after this had happened, that this is what will ultimately power the world. It may not be today, I mean 1954, but maybe in 2054, it will be very, very important in powering much of the world's requirement of electricity. Okay? And and there are, of course, many significant things that happened subsequently, but I typically confine myself to up to the point where Daryl Chapin and they were able to obtain the 6% solar cell. Okay? Now, what's also very interesting to know that all of these things, like for example, how nuclear fission got discovered. It was basically in trying to understand the transuraniums. Okay, and this whole business of whether it's a transuranium or not, and ultimately in trying to figure all that out, people realized that it's actually a fission where two more or less comparable sized fragments were being created from uranium once the neutron strikes. Now, similarly, over here, what people were very interested in, was this whole application of rectification. So, once the AC power had been invented, and much of the credit for that must go to Tesla. After that, people wanted to know, I mean, is it possible to rectify it so that only one part of the wave shows up? Because, once you could do that, then, you could actually separate signal from noise, and be able to capture different kinds of important signals, and that's really how everybody got interested in it. And the person who discovered, this rectification, we have seen about the thermionic emission, okay, and that also gave birth to the rectifier, okay, but this actually precedes that, and it was known as the point contact rectifier. Basically, what this person, Ferdinand Braun, had shown is that if you take just I think it's a lead sulfide, galena is lead sulfide. If you take a block of that, and if you just touch a wire, to the galena surface, that there is a rectification of the signal, and so he got the Nobel Prize for that, the point contact rectifier, and along with him, the person who got the Nobel Prize was Marconi, who's credited to be the discoverer of or inventor of the radio. Okay, bit tragic for one of our Indian scientists that he didn't get it. Okay, I'll explain why it's a bit tragic. Okay, so that was an important thing that they had done. Ferdinand Braun and primarily. Okay? Now this is our J.C. Bose. Okay, college professor, not even. I mean, he was in Presidency College in Calcutta. J.C. Bose was an amazing inventor. Very very creative mind. Okay, and what he did was he is the person who, for the first time, uh, applied this, okay, to radio waves. You know that the electromagnetic spectrum, of course, covers all the way from X-rays to extremely long waves. This is where your radio waves come, and so Bose was able to show that bronze rectifier actually helps him to rectify radio waves. There's a myth in India that Bose was abhorrent about patenting. It's not true. This is his patent. I'll send you the patent if you want. Okay, and so he did patent it. Not what I read when I read the patent. I didn't find it absolutely focused on the radio wave, but it was more generally talking about detection of electrical disturbances. But the fact is that he is the one who's credited with detecting the radio waves for the first time. But it was really Marconi who made a practical device out of it. Okay, now this is how that Galena system is. So you have that lead sulfide somewhere here, and you have a wire. It's so fragile. This thing, it looks like a cat's whisker. That's why it's called a cat's whisker detector. So this is the kind of thing which you just kind of touch on the surface, okay, and it rectifies the signal. Okay, that's what uh, Ferdinand Braun had found, and Bose showed that it also happens for radio waves. Okay, but the problem was that it's such a fragile looking thing, that people knew that this cannot be commercialized. It's okay doing a laboratory experiment and getting students to see it and that kind of thing, but it wasn't a practical device. Okay, and it was really in trying to get this kind of a practical device that the tungsten wire based rectifier became quite popular. Okay, uh, but we'll see what were the limitations with that. And so, this is the thermionic emission, which you have already seen when we discussed Langmuir's lecture. Okay. And this was not bad. And you can see the date, 1904. This was made, whereas Braun, okay, you can see 1874, when the point contact rectifier was made. And so was J.C. Bose's thing, 1904. So much before really this or around that time when basically this Bose had identified that the cat's whisker can detect radio waves. Around that time, these people had shown that this kind of that thermionic emission vacuum diodes, do more or less the same job, and they were very rugged. So that's why nobody was taking the point contact rectifier that seriously, and people moved on to the vacuum diodes. The early radios and all were all based on this technology. Okay. Now, then what happened was that the work on this did not stop. The work on rectification. When the Second World War was kind of brewing, uh, the Britishers and already aeroplanes and Germans had already developed a good fleet of war planes, and which could carry large bombs, and so there was a lot of fear that the Germans will overrun everybody, and so the Britishers, smart thinking people, they said we must find a way of shooting down the planes. I mean, that's what they would have said. Okay? And then, of course, they conceived the radar. Okay, and if people say that if the Second World War was won by the Allied forces, it really must be credited to the radar, because the Germans were completely taken by surprise. They did not imagine that the planes, would just get shot down. They had no idea, about the radar. And but what happened? I'm telling you the final story. But the problem was that the radar required operation of these rectifiers of microwave radiation, microwave frequency. Okay? And that's something that these things could not do. This could not do. It was fine for the radio wave, but when they tried to apply it, to the microwave part of the electromagnetic spectrum, it did not work. And so, what would people do? Because everything else had been figured out about the radar, except that they didn't have the detector. And so what then they did, world over, is that they said that let's go back to square one. Okay? Let's go back to all these point contact rectifiers and these kinds of materials and see, if it is possible to solve the problem. Okay? So around that time, I think it was Westinghouse Corporation. Westinghouse had done some of the most pioneering work, with silicon, and they had shown that silicon is also a very suitable point contact rectifier. And I think it was easier for them to fabricate devices out of silicon than with lead sulfide. And so there was a huge amount of work, especially in the US, on trying to look at how to improve the rectification properties, of silicon. Okay, and that finally was successful, you know, and that then is what really led to this kind of microwave frequency detection and gave birth to the radar. Okay, but one thing was there when they were looking at this rectification, they found there were huge variations batch to batch. you know, and later on, they figured out that it has a lot to do with the purity of the silicon. You know, so there was a tremendous effort, which was made to try and kind of make like 100% pure silicon. Okay? And that's really, they said, let us first make 100% silicon. After that, in case there are some impurities, etc., which are acting on these things and giving the response, we will look at it at that point. But let us really try to purify, silicon. Okay? And that's what this person was doing, Russel Ohl. He was an electrochemist, okay? Russel Ohl. Uh, and I mean, okay, and he was hired in by Bell Labs. Was obviously a very decent scientist. Okay, and Russell Ohl was given the job of purifying, the silicon. Okay, that's what he was doing. And how was he doing that? He was doing that by the standard process that is very common in metallurgy, which is zone refining. So you take some ore and fuse it, and the impurities tend to move to the two sides, and then that's how you constantly start purifying the substance. So that's what he was trying to do. He was fusing the silicon, probably cutting the two ends up, and again taking the middle portion, fusing it again, and that's how he was basically purifying the silicon. So let's read what it says over here. In the mid 1930s, Russel Ohl, an electrochemist at Bell Labs in New Jersey, began investigating the use of silicon rectifiers as radar detectors. He found that increasing the silicon purity helped improve the detection ability. On 23rd February 1940, he tested a small silicon slab that yielded strange, surprising results. When exposed to bright light, the current flowing through the slab jumped appreciably. He also noticed that different parts of the crystal yielded opposite electrical effects when tested with a cat's whisker style probe. Basically, in making some very detailed observations, he came up with the PN junction. And once the PN junction had been made, this person William Shockley, who was also working in Bell Labs, then along with Bardeen and Brattain, they are the ones who ended up making these transistors. Okay, so I mean, one invention gave birth to both the PN junction and the silicon solar cell. Okay, now and you can see, yeah, Bardeen, Brattain, and Shockley. This Shockley. Okay, and by the way, Bardeen got a second Nobel Prize for explaining the superconductivity effect. Okay, so he's one of those rare people who has been awarded the Nobel Prize twice. Yeah, and all of them were working in Bell Labs. It was a fountain of invention. I mean, if you all are looking for a conducive environment to work, this is one of those, because I'm sure there's such intense discussions and activity that take place, and they have got very very strong linkages with academia. No, and you can see I've just taken the Nobel lecture of Brattain, one of the Nobel laureates, and what he says over here is that I would like to first, in acknowledging people, I would like to mention R.S. Ohl, J. Scap, and H.C. Thurer, whose pioneering work on silicon made a new class of semiconductors available to physicists. It was Scap and Thurer who, as metallurgists, supplied the silicon and germanium with which we worked, and Ohl, who first discovered a PN junction in a melt of silicon. Okay? So that's you can see that truly he was the person who invented the PN junction. Okay, and then gave birth to both the silicon solar cell and the transistor. Okay? Now, what I will do is that I will read to you from Ohl's patent. Let me also tell you that this is something I've been noticing over and over again. Okay, that actually when you look at it, what you find is that some of the most fundamental inventions were actually not made necessarily for the first time by the people who get the credit. Okay? Like the Russians, this person had actually reported the PN junction in a cuprous oxide system more or less around the same time as Ohl had done. And I'm sure he did it independently, this person. Okay. And, but, this is again something that the dominance of the media, and all of us, we only, like, we are very much into the English language medium, So that's what we read. These people just do a lot of work after a finding has been made, and then they kind of start owning the invention when maybe they were not really the first people. Okay? But in this particular case, it was more or less around the same time. So let us see what actually Ohl says, in his patent. By the way, this is another thing. These patents, and I'll send you Russel Ohl's patents, are a few pages. Okay, there is a patent we'll later on discuss about a page, page and a half at most. And look at what they're saying. I mean, in that patent, okay, I mean, there is such important things that it covers the birth of both the solar cell as well as the PN junction, and only a few pages. Okay, so if I have written in the question paper that your answers should be brief and to the point, that's what I mean. I mean, you don't have to write a lot. You just have to write the essence, okay, of what it is. Because I mean, that if these people can do it, I suppose all of you can as well. Okay? All right. So let's see what he says. During an investigation of the production of fused silicon of high purity and its use for point contact rectifiers, applicant discovered that under certain conditions this material was sensitive to visible light, generating an electromotive force independently of any applied voltage. The light sensitive effects were of a magnitude comparable to the most effective photoelectric substances then known. The manner of the discovery was briefly as follows. This is wonderful because he's actually helping us to understand the discovery process. Not just, I meet this, I meet that. A considerable number of melts of pure silicon had been made up in connection with the above mentioned investigation. The material for some of these melts had been heated in a dry helium atmosphere. Okay, why did he use a dry helium atmosphere for heating?
So no reaction would occur.
So what would happen if you use nitrogen? Well, silicon nitride is you can form, right? So when we say inert gas, it just depends, on what you're reacting with. Okay. So probably, of course, he doesn't say anywhere. I suspect that he used helium because he could not use nitrogen. It would form silicon nitride, and obviously you are using an inert gas because you are trying to prevent the formation of silicon oxide. Okay.
So
So
also, like the impurities that he identified, like phosphorus and boron, which he called as impurities, they may also react with nitrogen, right?
correct. No, no, no. They could also, but that he didn't know at that time, no? He had no idea what was everything. Okay. Uh, I mean, he did not know the specific impurities at that time.
Okay.
But that's a very good point. I think this is the first time someone has mentioned, and frankly, I did not think about it. But I'll put not only uh, silicon, but uh, but possibly impure or but impurities in silicon uh, may react uh, with which is pi. The inert gas used was helium. Okay, which was much more inert. Helium did not react with anything. That's very good. Okay, and then he says the material for some of these melts had been heated in a dry helium atmosphere. From each of a plurality of ingots resulting from some of these melts in helium and melts. Why? As I told you, the melting must be because they were trying to do zone refining. Okay, that's it. And try to get a middle section which is the most pure. Okay. The material for some of these melts had been heated in a dry helium atmosphere from each of a plurality of ingots resulting from some of these melts in helium. A cylindrical rod had been cut for the purpose of making specific resistance measurements. These rods were about 3/4 inch long and 1/8 inch diameter. So we are not talking about any nanotechnology. Huh? We're just talking about a block of silicon being heated in helium, and then from that, he's drilling out a cylinder of silicon, okay, and then basically looking at the point contact rectification properties, maybe at the two ends as well as in the middle. That's the kind of work he was probably doing. Yeah? The rod from one of these melts had been equipped with metal end pieces by a rhodium plating and lead tin soldering process hereinafter to be described to provide a good connection for the specific resistance measurements. So you have to make an ohmic contact. Without an ohmic contact, you can't make the measurements. Okay, so that's what he was doing. With this kind of a lead tin soldering or rhodium, he was basically creating the ohmic contact. Such a measurement was being made on this rod by applicant when he noticed while viewing on an oscilloscope the wave shape of the 60 cycle current flowing through the rod. So it was an AC, 60 cycle AC, which he was basically passing as the current, okay. And because the 60 cycles, too fast, so he was looking at it in an oscilloscope, okay. Whatever changes, etc., in the magnitude of the wave or the shape of the wave and things like that. While viewing on an oscilloscope, because they were wanting to do rectification, right? So they had to basically see, if one side of the wave is getting cut off, which they could do it with an oscilloscope. Right. And wave shape of the 60 cycle current flowing through the rod, that the current in one direction was affected by light from an ordinary 40-watt desk lamp. At some point, when he could not figure out, okay, what has happened, okay, he just switched off that light. Okay, and then he realized, yes, this is what is affecting my results in the oscilloscope. Okay, and and so that's how really the invention happened. Okay, we'll read it once more. Such a measurement was being made on this rod by applicant when he noticed while viewing on an oscilloscope the wave shape of the 60 cycle current flowing through the rod, that the current in one direction was affected by light from an ordinary 40-watt desk lamp. Now, then what he did is that he replaced the he had connected it earlier to the probably the electrical mains, to the socket, and he disconnected that, and instead he connected it to a battery so that he was getting a DC power, from the battery. And what he was using was a rotating shutter, the shutter is going round, and uh, effectively, he just wanted to see what is the effect of light. So when the shutter is going round with a 20 cycle interruption, so obviously at some point, there would be light going and hitting the silicon, and other times it would be blocked. Okay, so I'll have a dark light response. And then he says a battery was then substituted for the 60 cycle current source, and a rotating shutter was held between the rod and a lamp to produce 20 cycle interruptions. A substantially square top wave form was seen by applicant in the oscilloscope, where wherever whenever the hole was aligned, and the light was passing through and hitting the silicon, they were getting a response. Okay, and otherwise, there was no response. And this is also very interesting. See, first he had the AC power, then he switched over to a battery. Okay, and actually the third experiment is not so easy to conceive, but I have a feeling that it would have been an experiment which would have probably made him the act of ridicule, by his colleagues. He said, "Hey, why don't I do one thing? Let me just get rid of this battery altogether." And I'm sure his colleagues or someone over there would have said, "What? You're going to get rid of the battery, and you're expecting a wave in the oscilloscope?" They must have laughed at him. Okay, but that's exactly what he did. Upon reduction and finally the elimination of battery voltage, the square top form persisted, although at a reduced amplitude. So there was an effect of the electrical bias, but it was still that even with the battery off, he got a signal. Then he says this entirely unexpected phenomenon was recognized as of possibly great importance in the art of light sensitive electric devices, and further study of this phenomenon was undertaken forthwith. The outcome of such study is that improved light sensitive electric devices, and particularly photo EMF cells of high sensitivity and great stability. The stability is something they always emphasize. The silicon is so stable, they kept on saying stability, stability. And great stability have been made available. The present invention is a result of the above mentioned discovery. So you can see more or less in a couple of paragraphs, the discovery process has been very nicely stated. Okay, and when you write your patent, I've seen a lot of people say, you should write your patent in as cockeyed a manner as possible, so that no one can figure out anything. I can tell you this much: all the great patents that I have read, they're absolutely clear. What I then understood, okay, is that actually what happens is that if you have something really remarkable to report, you just report it fairly and squarely. It is the guys who actually don't know what they've invented, or who have almost like done nothing, just a copycat kind of a thing with a little bit of variation here and there, that those people write in those funny manners their patent, you know, not these pioneers. Pioneers write with great clarity. And you'll see this over and over again, when we also look at other patents. Okay. Uh, Now, that what I mentioned to you, okay, was the photovoltaic part of it. And mind you, his patent really revolves around that. It revolves around the photo effect. Okay. But look at how powerful his observation was. And I think that this is what makes Russel Ohl stand out from the crowd. You know, otherwise, when I saw what he did, it all appeared quite routine to me. But look what he did. So he was actually taking silicon in a crucible. Okay, obviously silicon melts at a high temperature, 1410 degree C. Okay, right? Uh, 1410 degree C. So you need a crucible, obviously, that can withstand high temperatures, something like 17, 1800 degrees. Okay. And so he put it there and he was heating it. And as I told you, in the zone refining process, you expect that it will move to the ends, okay, the impurities. Okay? Now, when he got this square wave, looking a bit sharper, okay, and then he took this cylinder, okay, and must have looked at it with a microscope, okay, and what he found is that one side had these kind of pillars, this part. The middle was like layers, there was some kind of a striation, and the bottom part was basically quite uniform. And so this is what he got, and this is the cylinder that he had taken out. Okay, this cylinder for his measurements, and these are the ohmic contacts that he was making, okay, with this, and that's what he was studying. Okay. Now, what happens is that, you see, because he was connecting it to a battery, so he was he knew how which way the battery is biased. Okay, so what he found is that, for example, when the negative pole of the battery is connected in one way to this cylinder in one of the directions, there was no current, okay, and in the other direction there was a current, okay, and because we know that the electrons will repel each other, so the negative pole will be repelled by at this point, and so he called this as N zone, which means that this is the negative zone, okay, and so this was there, and likewise he called this other one as the P zone, which is the positive zone. So it was the positive zone and negative zone based on how the battery is connected to this cylinder via this ohmic contacts. So that's really what he was doing, and that's how he called it as NNP. Now, I must also tell you um, that what really happened, obviously there was some kind of a, segregation of some impurities, in this, okay, in these two parts, that's likely what happened, okay, and so this is again something which is worth mentioning, that this is an important area, okay, like you start with something which looks uniform, and you create non-uniformity out of it, okay, uh, something uniform, make it non-uniform, okay? We will encounter this a lot more when we talk about the TRIZ methodology later on, okay, and so like, say, for example, this is when you make a lot of these paint surface coatings, okay, what can happen is these paint surfaces sometimes tend to blacken, because of fungal growth on the surface. It's quite a common thing which used to be there before, and now it's a lot less because of interventions by the paint companies. Okay, but and the way they have solved the problem is really by applying biocides, on the surface, so that these fungus, etc., they get killed. Okay, as soon as they are in contact with these biocides, and therefore they don't grow. Okay? Uh, Now this is a very interesting paper where uh, they actually start with a uniform paint, okay, which they apply on the surface, and while it is still wet, the biocides kind of go and bloom, all right, to the surface, and that is done by maybe incorporating certain fluorinated polymers, into the paint, and those tend to move to the surface, and along with it, they carry the biocides. So it's a very nice way in which you can do what is known as self stratification. Okay? That's exactly more or less the same kind of thing which happened in the case of the silicon. Okay? Now, so what later on, you see, these are not things that Ohl really was able to understand well. But the subsequent people, who got the Nobel Prizes, that they were able to figure out that what exactly is going on, with this particular thing that Ohl had made, and so I've tried to show it to you pictorially, that, like, for example, if you are, let's say, connecting let's say this is the N type, by that time they figured out that, one side, the negative side, had certain kinds of components which would have probably left free electrons, like we know, if you take phosphorus with silicon, because phosphorus is pentavalent, and it will want to look like silicon. So it can do that by going into the phosphorus state with the release of a one electron. So it will become N type. And likewise, if you move to the left of silicon, let's say you go to boron, okay, so boron is electron deficient, so it will want to pick up an electron, okay, and it will then create a hole. Okay? And so this would be a p type, where there would be a hole. Okay, so if I were to look at the negative pole of the battery, okay, and in contact with the N type part, okay, so effectively what will happen is that the electrons, would get repelled in this thing. So the electrons would get pushed, deeper and deeper into the bulk of the semiconductor. Likewise, since the positive pole is in contact with the p type, side, okay, the holes will get pushed deeper and deeper into the bulk. Okay? So effectively, this is what will happen. Okay. Now, what uh, happens prior to this, okay, is that, suppose, let's say I had, he had found this thing over here, this layer. So they wanted to know what is this stuff. Their reasoning was that, look, I mean, if electrons and holes see each other, what will they do? What will electrons and holes do if they see each other?
They will come by.
They will combine. Okay. So, the ones which are closest together, the electrons and the holes, they would probably have combined, and now I've lost the electron and hole, and so over here, all I will have is the fixed carriers of charge. There would be no mobile carriers of charge. Okay. And so this part would be depleted in the mobile carriers, and that's why it is known as a depletion layer. Okay. So this is the depletion layer. You can say, then why doesn't all of them do this? The reason is because the moment they have recombined, this has now become electrically insulating, because there is no mobile carrier to carry the charge. Okay, so it can only happen in a thin layer, this kind of a neutralization, and the electron rich part the rest of it will be there, and the holes will be here. Okay? So effectively, this is like your starting point, and now I'm biasing it with a battery. Okay, so when I do this, As I told you, the electrons will get repelled. They will start moving to the bulk, and this also the holes will start moving to the bulk. Now, what happens is because I've applied a power, a voltage, across this cylinder. So what will happen is that naturally it will continuously see electron and hole, and they will recombine. Okay, and so there is no problem. In other words, the depletion layer has got narrowed down, and it completely disappears. If you have a voltage of around 7.7 volt with the negative terminal connected to the inside. Okay, and so this then allows for a continuous flow of charge, in the circuit. Okay, and that's what is the forward bias. Okay, now on the other hand, suppose I connected the other way around. What will happen is, now I've got my hole. Okay, I've got my hole, and I've got the electrons here. This is the negative pole. So the holes and the electrons, they will get attracted to each other. And so what will happen is that gradually, some of the holes will start moving into the battery. Okay, and it will expand the depletion layer. And likewise over here, the electrons will get attracted to the positive terminal, and so they'll flow over here, and so this whole thing gets expanded, the depletion layer. In other words, no current can flow because if anything, I've expanded my depletion layer where there is no mobile charge, and therefore this is the reverse bias. So this is what the way in which Ohl was able to figure out. Like for example, he of course loosely called it P and N, depending on whether current was flowing or not. Without much of an understanding of the intricacies of what is a depletion layer, etc., etc. Now, what then was happening when you have photo illumination in this? What would happen if I, let's say, took this, okay, and I illuminated it with light?
So the electrons will become available from the depletion region because of the photoelectric.
Wonderful. Okay. In other words, electrons will become available means you will create an electron hole pair. Okay.
Yes.
So that's what you'll do. You'll create an electron hole pair. Okay. But make a note of this, that the light has to penetrate into the depletion layer, okay, for the electron hole pair to be formed. There's no point in forming an electron hole pair either on the N side or on the P side, simply because they're already, rich in electrons and rich in holes. So generating an electron hole pair there would not make any difference. What would really make a difference is that if I were to generate the electron hole pair in the depletion layer. Okay. So that's effectively what is happening, that there is this electron hole pair that is being created. Once I've created the electron hole pair, there's no problem. Okay. Then the current can flow continuously. Okay. And, that's what it is, So I've got my photon getting absorbed. Okay. And this is the hole, this is the electron. The electron is basically moving in this circuit. Okay. And again, flowing in the external circuit, coming back here, and again it will combine with the hole, recombine. Okay. And so light is continuously generating the electron hole pair and thereby helping to move the electrons in the external circuit. Okay. And that's how you are creating the photo EMF. Okay. So that's the sum and substance of really how exactly the photovoltaic cell works.
Sir,
Now, yeah,
sir, in that diagram, like why is there any reason as to why the P type is much thicker than the N type layer?
brilliant question. Uh, I'll come to this part. The rest of the second invention pertains to this. Okay. Uh, But over here, it's only a schematic representation. You understood? Huh? It's only
Okay.
a schematic representation, but I will explain to you that you've actually asked a very, very good question. Okay? Let me also tell you that this image that I took is from a latter day invention, okay, which I will explain to you. You know. But this is not exactly the configuration which Bell Labs worked on. Now, what did Bell Labs actually work on? And once they realized, that what really is the sum and substance of the entire phenomenon, okay, the first thing that they realized is that they must make this N type, not N type, in their case it was P type, okay, that this layer, so Bell Labs had a block of N type, and over that they had a thin layer of P type. Okay. Now, what did they what were they first trying to do? The first thing is that they had to keep the thickness, of whichever thing was in contact with the light over here, the incident light. They had to keep it as thin as possible so that the light can penetrate into the depletion layer. Okay, so they understood that, and they said, Ohl's configuration does not allow for that to happen. He would have had a pretty thick layer, and so we know what is the wavelength of light, what is the kind of maximum penetration depth that you can have for a particular wavelength. So the way the Bell Labs, had fabricated their device was that they had a block of N-type semiconductor, which they first made. Okay, huh. And over that they introduced the P-type. All right, that's what they did. And later on, people just reversed the configuration. They started with a block of P type, and over which they made an N type. That's a finer difference, and I'll explain to you why that was done. Yeah. Now, and the people who did that and who got the patent is Chapin et al. Okay, and Chapin et al. Very beautifully describes, what was the motivation behind their further work? What is it that OL had done and which they basically improved upon? Okay, and how they were able to get a 6% efficiency. I presume OL did not get more than a percent or two at most. And not only that, this patent, when I was reading the whole patent, it's amazing. Everything that we do today is not really much different from whatever they had said in their patent. It's a remarkable patent, and it's so good that I thought I'll read out, the whole thing to you. Okay, just so that you can appreciate it in their own language. The choice of silicon as the semiconductor material provides certain initial advantages. So, why silicon was taken? Now, remember, they were not actually working on point contact rectifiers as the focus. The focus shifted to in two directions. One was the manufacture of transistors, and the other was manufacture of photovoltaic cells. You know, and for the photovoltaic cell, they found that silicon is the best material, whereas for the transistor, they worked on silicon, they worked on germanium, there were other things as well. The choice of silicon as the semiconductor material provides certain initial advantages. Silicon is plentiful, being next to oxygen the most abundant element in the Earth's crust. Moreover, the use of silicon facilitates the problem of minimizing reflection losses. Okay? So what happens is silicon has a very shiny surface. So when I've got light is not necessarily always going to penetrate. If it acts like a mirror, it's going to get reflected. And if it reflects, then there's no point. Okay? So what they had to do was minimize reflection losses. Okay? And so what he says is, on exposure to the atmosphere, even in the absence of a protective coating, the silicon surface will acquire a transparent oxide coating because it will form silicon oxide, a very, very thin layer, okay, which will have a refractive index intermediate between that of the atmosphere and that of the silicon body. And that was known to physicists that if you have a intervening layer, with a refractive index in between that of the atmosphere and the main substance which you are illuminating, that reflection losses tend to be minimum. Okay, and so he says, and that of the silicon body whereby reflection is minimized. This tendency of silicon to form a protective coating of its own makes it unnecessary to provide heavy protective coating. So two purposes were served. One was that the reflection losses were minimized, and secondly, you see that silicon is vulnerable to attack, you know, but because of the formation of silica, a very, very fine, like a monomer, that it prevents the further degradation of the silicon. Not very different from aluminium. Aluminium has an external surface of alumina, okay, and that's what keeps the metal still shiny and glistening. Okay? Additionally, silicon is very stable at the temperatures normally to be expected in this use. And what were the temperatures? If you're talking about a solar cell, you're talking about temperatures of maybe around 0 to maybe 60 degrees centigrade or 70 degrees centigrade. So in that temperature range, did not find any significant instability of the silicon. Now, but the big invention was what is there in the second paragraph. Okay? What they did, is that by the time they had understood that p-type and n-type, they understood that things like phosphorus give you n-type, boron gives you p-type, and what they did was that they started with a block of n-type semiconductor. Okay, and then, as I told you, they tried to grow the p-type over the n-type. Okay, and so that's what they did, and boron was a perfect dopant, to make the p-type. Okay, and what the reason for that was that these people, another group in Bell Labs, CS Fuller, they had already developed a technology, for diffusing boron into a silicon from the vapor state. Okay, and they could diffuse boron into an n-type semiconductor. So I've got an n-type semiconductor, boron starts getting diffused. Initially, what will happen is boron will diffuse and I'll start creating the electron hole recombination and I'll start creating a depletion layer. Okay, when I start diffusing more and more boron, then what will happen is that beyond a point, it will only be like a p-type semiconductor. It's not going to keep recombining. So that's how they were able to basically create a depletion layer in the middle, followed by the p-type semiconductor over the n-type. So he says the choice of boron as the significant impurity in conjunction with the silicon body to form the p-type surface layer provides further important advantages. As described in application serial so and so by C.S. Fuller, techniques are now available for the diffusion of boron from the vapor state into an n-type silicon body to form extremely thin, uniformly low resistivity p-type surface layers. Now that was a huge thing that they did, because in doing that, they now could let the light penetrate into the depletion layer. This makes feasible a p-type layer sufficiently thin to be nearly transparent to the incident radiation and of sufficiently low resistance to avoid high internal losses. Now, what was very, very interesting, is, and he explains this in the next few lines. Additionally, it is found convenient to electroplate directly to the thin, smooth boron diffuse layer for forming a low resistance ohmic connection there too. Okay. Now, what he's trying to say is, look, the way they were earlier making their ohmic contact was that suppose I've got a layer, you know, then they used to roughen up the top surface by doing some kind of a sandblasting or something like that, and then the ohmic contact, which like a silver or rhodium, whatever alloy, would nicely stick to the surface. Okay, but because they made the P type so thin, there was no space to do sandblasting. You know? And but what they found is that on this boron diffused silicon semiconductor, the rhodium forms a beautiful ohmic contact without need for any sandblasting. You know? Because if you did sandblasting, I would have had to start with a thicker layer and blast off a part of the surface, and that would then increase the internal resistance of the cell. Okay, so that's what they are basically talking about. Okay, additionally, it is found convenient to electroplate directly to the thin, smooth boron diffuse layer for forming a low resistance ohmic connection there too. This is in contradistinction to various other types of impurity diffuse layers, which have required sandblasting as a prelude to electroplating, an expedient not convenient here unless measures are first taken to build up the thickness of the p-type layer. Okay, finally, it is found that a boron diffuse layer of this kind is extremely stable, resulting in reliable operation over an extended life. So I hope you can understand that they were also something like BASF. One group, excelled in doing chemical vapor deposition. Another group in fabricating cells, another group in electronics. Okay, so they could take advantage of all their complementary skills. Okay, and so I will say that this was probably the most important part of their patent, and which allowed them to achieve something like a 6% efficiency, of generating electricity. Okay, I'm not going to read this out, but I do expect that you all will read it. Now, there was another very, very important thing which they noticed, when they were working on this cell. You see, what they realized was that, okay, I'm generating power. Now, what am I going to do with this power? So they had to connect a battery to it. And so the power was being drawn by the battery. Now, what they found is that when we are in the active mode, that is, light is falling on the panel, or on a cell, and is generating current, and the current is being stored in a battery. There's no problem. It's happening with a low resistance, and they can nicely charge up the battery. Problem was that, you see, when it is in the dark, the cell, so there's no current flowing through the cell, because I'm not generating any power. Now my battery is my active element. Okay, so the battery starts flowing current, in the circuit unnecessarily, and there is a loss, of the power from the battery because of this. So they circumvented that problem, right, by introducing a diode. This diode basically blocks the current in the direction from battery to cell. So let us see what it says. It is characteristic of these cells that when active, the induced current flow within the cell is in the reverse direction. As a result, when passive, these cells will be biased in the forward direction. Okay, so what happens is, in other words, you can see that what we are talking about, is really like having something in a reverse bias, and operating it, okay, in one direction, and in the other direction it will be in the forward bias. As a result, when passive, these cells will be biased in the forward direction or direction of low resistance by the charge battery 30. and so represent a low resistance load there too, which tends to drain the battery. So effectively, the battery was getting discharged by the cells, you know, because it was in the forward bias when the cell is not generating any power. To obviate this difficulty, it becomes important to insert in series with cells 10 and battery 38. They're the cells and this is your battery. A unilaterally conducting element 31, this one, for example, a crystal diode poled to provide a low resistance to charging currents developed by the cells, but high resistance to any discharging currents from the battery through the cells. You know, so by that they were able to prevent the self discharge of the battery. You know, and in the direction when light is falling and current is being generated, there was no problem. They could charge up the battery. Okay, so that was another very significant finding. Okay, and just to tell you what is the thickness of their p-type layer, you know, which they had used, it was something like a 2.5 micron p-type surface layer. So you know what is the wavelength of visible radiation, you know, and so a substantial amount of the radiation could actually go penetrate into the depletion layer and cause the electron hole pair generation. Is that clear to everyone? Anyone who is not understood? All clear?
Yes, sir.
Yes, sir.
Okay. Okay. Now, and then, you know, what he did were, of course, straightforward things which are known to electrical engineers, you know, but it's remarkable that they pointed all of this out in their patent. Okay. Firstly, an individual cell like this generates about 0.52 volts. Okay. That's what they found. And they said, look, we will require to generate large voltages, large current, you know, and they made use of the standard knowledge, you know, that if I connect up many of these cells in series, you know, that I will be able to add up the voltages. Okay, so and if I connect up many of these things in parallel, then my effective resistance, you know, will go down because 1 over R is equal to 1 over R1 plus 1 over R2, etc. You know, and so my effective resistance will come down. And when my effective resistance come down, you know, V by R is equal to I, my current goes up. Okay? So to basically generate high voltage plus high current, they connected up, you know, many of these cells in series as well as in parallel. You know, and by the way, this is one block, you know, and you have in a solar cell many of these, you know, many of these repeating kind of units, and this whole thing would be a module, and you decide you want to make a module with what kind of a wattage output. Okay? So he says a single solar cell gives an output voltage of only about 0.5 volt. However, a typical 12-volt panel about 25 inches by 54 inches will contain 36 cells wired in series to produce about 17-volt peak output. Okay? If the solar panel can be configured for 24-volt output, there will be 72 cells so that two 12-volt groups of 36 each can be wired in series, usually with a jumper, allowing the solar panel to output 24 volts. When under load, this voltage drops to 12 to 14 volts, resulting in 75 to 100 watts for a panel of this size. That's what they use today. It's all in their patent. Multiple solar panels can be wired in parallel to increase current capacity 1 over R1 plus this. Okay, so that's what it is. Okay, now, so this is what Chapin et al. Did. You know, they took forward the work of Ohl, took about a decade and about a decade, 10 years, you know, and really improved. And the most significant thing was that they could build up a very thin layer of the p-type cell in an extremely clever way. Okay? Now, let us see some of the further things that were done. Okay, 1958, Bell Labs produces solar cells for space activities. 1953, okay, there was more work, on different variants of the cell. 54, Bell Labs announces that they have been able to make a cell with 6% efficiency. And, in that year, 1954, the New York Times forecasts that solar cells will eventually lead to a source of limitless energy of the sun. It's still not happened, but certainly, there's a huge kind of impetus on solar at present. 1955, Western Electric licenses commercial solar cell technologies. Okay, and that's interesting, and we'll look at the prices, etc., later on. Okay, now this is the significant invention that happened subsequently. It was this company, US Signals, okay, who reversed the configuration of the cell. Instead of making a P type over an N type, they created an N type on P type silicon solar cells. So that's what I was telling you. That this I had taken from a later day picture. Otherwise, Bell Labs thing was N type with a thin P type. Okay, what I've shown you that figure is the typical thing that was done by US Signal. And why did they do that? They found that with this configuration, the cells are more resistant to radiation damage and are better suited for space. So the stability of the cells improved remarkably. Okay, now they were able to then increase the efficiency of the cell to something like 9%. And the first solar powered satellites were launched. Okay, and by 1959, they had already achieved about 10%. Now let me tell you that there's a lot of talk about efficiencies and all, but I can tell you that many of the cells that we have worked with, even in the last 10 years, have been typically, the average efficiency you'll get is about 14-15%, nothing more than that. So I cannot say that there was a huge improvement, which has been made. Okay, now let us also see, okay, that what are today some of the most efficient solar cells, okay, which are reported. All right, and so as you will see, most solar panels are between 15 to 20% efficiency. Okay, and even that is difficult to get sometimes. Okay? And these are the five which are considered to be important. Okay, so they have achieved, let's say, around 23%. Of course, this is data from 2019. Now, you might say 23%. How do I go to 100%? You can't. The theoretical limit for a solar cell is 29%. So if anyone tells you, no, with a silicon solar cell, I want to go to 100%, forget it, you can't. Can anyone tell me why? What is the problem?
One problem would be that not all, like only the surface will receive the light, right? Not all
No,
atoms.
surface means the radiation is falling on the surface. You are taking it with respect to the radiation falling on the surface, the efficiency.
Okay.
Anything else? Think.
Junction because of the depletion layer, because the thickness of the depletion
Well,
layer
that
will
is that
always
is
be there.
important. That's why to get even this 29% is difficult. Because there would always be some of the light which will fall not in the depletion layer, but it will be elsewhere where it is of no use. That's one. Anything else? Think more generally about light.
Sir, it is not available when we want it. Like it's only available from not
No,
even
I mean
sunrise
these
to sunset.
efficiencies are these efficiencies are for when it is there.
Sir, we need a specific wavelength of light for that.
Brilliant. Yeah, I know you'll give the answer. There isn't a complete match between the visible, why it is UV rays, UV rays, uh, or I wouldn't even say UV rays, between the electromagnetic spectrum and the silicon solar cell band gap. Okay, is that what you're trying to say?
Yes, sir.
Right. We'll come to this. Okay. Now,
Sir,
yeah,
sir, so like if that was the reason, then can't we like make some modifications in the structure so that we get much better compatibility?
very nice question. We will discuss this. Okay. Uh, I'll just put can overlap with the spectrum be improved through modification in structure. That's what you're trying to say, right?
Yes, sir.
Okay. All right. Very nice. Okay. Now, let me first show you, right, what a remarkable progress has taken place in solar photovoltaics. Uh, I'm not even going back to 1954. I'm going back to what? 2014. So I'm talking about roughly about say 8, 9 years. Okay, and you know, and I'll show you later on. This price in 1954 was something like $76 per watt. And then it was brought down to something like $4 per watt. Okay, and today, okay, it's around about $3 a watt. So there's been a further reduction of by about 25%. But let me tell you that don't get swayed by these prices. Prices can go here and there. So this may not. You might see later on again things climbing. Okay, so don't fall for it. What I think is important though is the significant change from $76, you know, to $4. Let me also tell you that if you were to look at the role of technologists and engineers, it must be coming here. People like yourselves must have done brilliant things. Okay, at the back end, may not be at the front end. You may not have got visibility. Okay, but at the back end, you could have done great things. Okay? Like, for example, I can make the cells. None of you asked this question. What is how thin can the solar cells be? Because there's a material input when you have to fuse silicon, to make a single crystal silicon. It's a very energy intensive process. People don't realize this. Like when people talk about renewable energy, and you talk about this, the initial energy input to make these things is huge. Okay, so you can say, I will power the whole world, but the amount of energy that you will require to even fabricate the devices is massive. It'll take you a few years to pay that off before you actually start generating some real power. Okay? So bear this in mind. Okay, but obviously there have been great contributions, all across by physicists, by chemical engineers, by chemists, by material scientists, and name it. All of them would have contributed tremendously. Now, the problems, all the problems are not over. Okay, some of the problems which still remain. Okay, One is like I'm just looking at it in the context of, let's say, India. Okay? Today, the Chinese are the world leaders in price. Okay? And if you really want to compete with them fairly, right? I mean, there's a huge amount of an improvement which will be required in our capability. Okay, uh, we'll have to make these panels much more lightweight. For example, if you want to extend it to space applications, you want to extend it to aeroplanes, whatever. Okay, the durability is a very serious issue. How long will these things last? Because when people are making these panels cheaper, we don't know if you're comparing apples with oranges. Okay? Maybe they're cheaper, but they won't last you for 20 years. Okay. Uh, Dust, all this efficiency and all these things people talk about, our atmosphere is extremely dusty. And in fact, people talk about putting these things in deserts and all. You can, but imagine if there's a layer of dust over the panel, your incident radiation will get cut off. So your efficiency will drop. And then there are many other auxiliary systems to think about, including the battery, the tracking devices. If you need to track, there are all kinds of things that you need to take into account. Um, this is the typical electromagnetic spectrum. Okay, so this is what the sun produces from black body radiation. Okay, this one. Where does silicon come? Okay? Silicon, itself only absorbs a part of the radiation. For example, anything which has a longer wavelength than the band gap is of no use. Silicon cannot absorb that radiation. And so if you were to look at all the kinds of losses, that's where the theoretical maximum of 29% comes in the capture by silicon. Okay? So what people have done is that they have tried to put sandwich cells, where, let's say, the light first falls on the indium gallium phosphide cell with a band gap of 1.86 electron volt. The, the whatever is of a wavelength which is longer than what silicon can absorb, it's absorbed by another cell, and then from that, it's absorbed by another cell. Okay, and like that, they have been able to basically make better use of the entire electromagnetic spectrum. Okay? And this is really how they have been able to achieve something like 45% maximum efficiency today. You have all seen that these solar panels are actually put in a somewhat slanted position. Okay? And so it's quite a important thing, all right, in really optimizing how exactly the sun's rays should fall on the panel. Okay? And that actually you ideally would like to always have it normal. The sun should be normal to the panel, so that it's falling as vertically as possible. Okay, and but that doesn't always happen. So that's what he's talking about. In field use, it will be advantageous to support the various cells in a position inclined to the horizon, the optimum degree of incline being related to the latitude of the site. Okay? It may be advantageous to utilize cells inclined by varying amounts to achieve an averaging out effect over the day. Okay, and so there is one extreme would be that if I'm having some kind of a tracking system and I'm continuously tracking the sun. Okay, but then those kinds of systems are quite tedious and costly, and so in fact people don't even put it for a day. You'll kind of take a average for the whole year and decide that what is the best slant at which to put the thing, so that on average you get the maximum amount of sunlight falling on the panel. Okay, and so So that is again, something that they taught us through their patents. And so just to give you an idea, this is, you can see, depending on whether it's winter or summer, these angles change, okay? And then different places on Earth which are at different latitudes, the angle will depend on that. I'll send you a few slides, which is separate. I didn't want to cover it in this class. Okay, it just goes a bit beyond the whatever we want to discuss. Okay, but I think it's a very, very important thing for you to know, and also because I see a lot of role, for especially engineers in understanding these aspects. That how do you optimize the performance of a solar cell? So you could have, for example, you can see if I'm continuously tracking the sun, okay, then of course I will get a maximum power output, okay, per day. And of course it will vary from season to season. It obviously, if I've got summer months, when the sun is the solar insolation is much higher, and compare that with winter months, it's of course going to be different. Okay, so but even so, what you can see is that when I'm continuously tracking, this is the kind of power output I get over a day, per meter squared per day. On the other hand, if let's say I'm optimizing it for the full year, at one go, and that's exactly what all of us do. We are just optimizing our panels, like in on the ICT rooftop. You'll see these panels; they're all optimized. Nobody is moving them around, and so you can see what is the kind of compromise that you're making. This is what you'll get. All right. Obviously, it's substantially lower than if I were tracking. So that's the kind of cost-benefit analysis that you need to do, while really setting up these panels. And then you could have also adjustments for every season. Seasonally you can track the sun, and so depending on how you want to do it. But this is really the one which is the most common. Sorry, the one which is the full year. This one, okay, the full year is this. So this is the one which is normally the most popular. Okay. Now there is a second thing, which he taught, and it's very important. Now let me ask you, what would really the power output from a panel be? What will it be dependent on? What are the variables? How much power you get out of a panel?
It will depend on the efficiency of the panel and on the intensity of the light that is falling.
Very good. So one is the efficiency of the panel. The other is the intensity of radiation. Okay. And the third, of course, is that it will depend on the area of the panel, right? So, of course,
Yes.
if you're normalizing it to per meter squared, then of course that is taken care of. Okay. But those are the things that you'll have to look out for. All right. Efficiency of panel, um, area of panel, and insulation falling on the panel. Correct? That's all right? Hmm?
Yes, sir.
Okay. So power output would depend on this. Okay. So that's great. Very nice. Now, in fact, what he says is that, you see, that is true if I let's say have the solar radiation falling on the panel, of course. But the question is, now let me ask you, is there any way to alter Efficiency, of course, once I put a panel, I can't change the efficiency. The area is also fixed. Is there any way to alter the insulation falling on the panel?
So that was by the angle, changing the angle. That is.
That is the optimization. That's right. You can optimize that. But let's say
So,
I'm operating at the most optimum angle. Is there
so
any other
there,
way?
there must be a way to converge the rays.
Fantastic. Okay. So you're talking about, concentrating the radiation, right? You know, and see, which means that all of you know, for example, that if I take a parabola, right, and a parabolic dish, okay, it always, it doesn't matter how the radiation falls perpendicular in which part, it will always focus to a point, okay, in a parabola. So what you can have is that you can have those kinds of reflecting mirrors, which are spread across large areas. Okay, and your panel might be in a relatively smaller area. Okay, and but all those beams are kind of converging, on the panel. Okay, and there is a way of concentrating the radiation, exactly as one of you said, not very different from taking a magnifying glass and concentrating the radiation and burning paper. Okay, but that of course is a lens effect, whereas I can do it with the help of mirrors, and concentrate the radiation to something like a parabolic dish or a parabolic trough. And so, what he's saying is that it may be desirable additionally to provide some arrangement for concentrating the sunlight on the cells. A cylindrical or parabolic reflector will be helpful in concentrating radiation on the cells independent to some extent of the exact position of the sun. It will be obvious that whereas techniques of this kind can be employed to enhance the amount of sunlight incident on the cells, and then that's what it is. But what he doesn't say is that there can also be some problems of doing this. Can anyone tell me what could be some of the anticipated difficulties?
Sir, it would cause a lot of heating up.
Brilliant. Okay. So one is, of course, there is an associated cost. Okay. Obviously, if I'm putting a tracking system or I'm putting mirrors over a large area, naturally, I mean, that increases the cost of doing things. Okay. But then you see, in earlier days, the cost of the solar panel was much more than the cost of, let's say, a reflector. I can take an aluminum foil and make a reflector out of it. I mean, it can be made quite cheap. Okay, so it would be much better, if we can do that kind of a concentration. Okay, but there are some other issues. So what did you say? You said there will be a heating effect because of concentrated radiation. Brilliant. And there would also be a cost involved in concentration, right? It's not for free.
Yes, sir.
Okay. Now, if you have this, what kind of a negative fallout are you expecting from the heating?
So the panel may get damaged due to it.
Panel may get damaged. Yes. Okay.
And also, like the surroundings would be hotter than normal.
Okay. So let's say uh, now uh, uh, panels may get damaged, excessive heating of the surroundings. That's what you said, right?
Yes, sir.
Also, sir, due to damaging of the panel, the
Huh?
efficiency of the panel will also, due to the panel getting damaged, the efficiency will reduce
Brilliant.
and overall
Due
effect
to
will
the
be same.
panel getting damaged, the efficiency will drop.
Yes, then the overall effect may result to be same if we are not putting any reflectors or concentrators.
Yeah, right. But do you think that efficiency can drop even without the panels getting damaged? Is it only because the panels will get damaged?
No, no, sir.
Right. There could be an intrinsic, right, effect of the current voltage profile as a function of temperature. Okay. Huh? So, yes, panels getting damaged would, of course, adversely affect performance, affect performance or life of module. But even if the panel does not get damaged, there can still be an adverse effect of temperature. Okay, everybody is clear about the difference between the two? All clear?
Yes, sir.
Right. Okay. So, let us, in fact, look at, right, what exactly happens, right, when something gets heated up. And so, for example, usually what happens is that all of these profiles of in a panel, okay, what we really have to look at is current. How much current are you getting, and how much voltage are you getting? Because the product of current and voltage is power. That's effectively what you're finally deriving from the power of the sun. Okay. Uh, Now, the two extreme ends are what we call short circuit current, where I've just shorted out the thing, okay, and you'll obviously maximize the current under those kinds of uh, short circuit conditions. And the other extreme is that when I have no current flowing through the circuit and it's an open circuit, and so I have what is known as the open circuit voltage. Okay. So those are the two ends, and ideally, okay, if we could have had, in reality, if we could have had the best performing panel, it would probably follow this kind of a profile. Okay. Not even this. The most ideal would be that I draw a rectangle, okay, from here to here. Now, what happens is that in reality, obviously the area under the curve which you actually get, which will always be lower than that rectangle. And so that really is the ultimate, you know, thing that you see as a consequence, or what we call as the efficiency of the panel, in terms of the power output from the panel. Now, when the temperature increases, like we saw for concentrating the radiation, what happens is that the current actually increases marginally with temperature. So it's not a bad thing. But there is a much sharper drop in the voltage of the panel. The output voltage that you get as a function of temperature varies inversely with temperature. If the temperature is too high, the voltage will drop, and that's what you can see increasing ambient temperature, what it does to the voltage and what it does to the current. So obviously the area under the curve will reduce, with temperature. So you may actually negate part of the advantage of putting in a higher insulation, okay, on the falling on the panel. Okay? And you can now, can anyone tell me how would you realize the best of both worlds? That is, how can I get a higher insulation and also without compromising much on the voltage drop? What can I possibly do?
Provide a cooling system for the panel.
Fantastic. In fact, this is great. Okay, that's it. Okay? So, logically, therefore, provide some kind of cooling arrangement, right? That would be nice. And in fact, there are certain things over here you can, by the way, there is also quite a bit of automation in this whole thing. There is something known as the maximum power point tracker, you know. So you can actually determine at which point, you get the maximum power point in terms of operating voltage and current, and these are things that one can buy today. It doesn't cost that much. If you have a large area of covered with panels, then it's not a very sizable cost. But if you have small units, then it's not practical to put such devices. Okay, so if, for example, you have got high irradiance and high temperature. Okay, so this is what that thing looks like. Okay, high irradiance and high temperature. Okay, and if I've got high irradiance and low temperature, you can see that you get a much better performance from the module. Okay, so this is really what one should try and do. That is, on the one hand, try to maximize the amount of light falling on the panel, and on the other hand, try and keep the panel cool. Okay? In fact, some of these things, what we found is, although theoretically, all right, you can see even from the time of Chapin, we are talking about the patent in 1954, these are known. Okay? But in reality, nobody was doing it. Okay? And in fact, I remember this something from our own work. A colleague of mine, Dr. Subarna Maiti, and I'd asked her to do this. And basically, in this thing, what was done was, on the underside of the panel, you can see there are, okay, so one was that there were reflectors which were put. Okay? We are not talking about the parabolic type of reflectors. These were just plain foil reflectors, which were put, and you could get something like maybe a 1.5 or maybe 1.7 times the standard solar insulation. Okay, through use of these reflectors. These are two reflectors. Okay? And so it was heating up the panel. Okay? Because of that. I mean, excessively heating up the panel. Okay, and at the bottom, there was a phase change material which was used. Okay, so it was a wax metal composite. So like in a workshop, you provide these metal turnings, right? So those metal turnings filled up the volume in a box like structure, and then you poured wax into it. Okay, and then the wax, of course, solidifies, and then what happens is that when you're operating it, because of the heat, the wax begins to melt. Okay, And so you have a phase change. That's why it's a phase change material. And you have to kind of take the amount of wax in a way that you can more or less, cover the peak period of insulation. When the temperature becomes especially high, and you can really control the temperature with those kinds of phase change materials. The sum and substance is that from the same panel, it was possible to get something like, I think, about a 1.4 times, the amount of output, power output. Okay, and so that's good because the panels were much costlier than these reflectors. Okay. Now you can also do something alternatively, like even if I do this, I'm really not making use of the heat, which I'm generating. I mean, it's just being dissipated at night, and again the wax is solidifying, but you're not really making use of it. You could also consider putting water pipelines, under the solar panel. Okay, and you can use the water as the cooling agent, and so you can keep your panels quite cool that way. In fact, this is the first solar powered reverse osmosis plant in our country, which was set up in 2006, in Rajasthan by my colleagues and myself, and along with a organization called Barefoot College, and then these these pipelines were put, and this module, what it was doing was that it was being used to actually do the reverse osmosis. Okay, so it was generating the power for reverse osmosis RO plant. Okay, and so what was being done was that the feed water for the RO, was being passed from the underside, and so the water warms up a bit, and because of the warming up of the water, the membrane flux actually improves, provided you don't exceed a certain temperature, because then you'll spoil the membrane. But like, let's say if you're operating at 25 degrees centigrade, and if you're operating at 40 degrees centigrade, at 40 degrees centigrade, you will get a better performance. You'll get a higher flux. So you gain twice over. One is that you generate higher power through this arrangement, and because the water is also getting warmed up, you can also get an improvement in the efficiency of your reverse osmosis process. It's become now quite popular. I was seeing, a lot of people have now started doing this. You can see these 2-in-1 solar panels produce electricity and heat. Okay, 120 liters of water per day. So I mean, you can actually therefore innovate. Okay, around the use of a panel, and just see what is the best thing that you need to do to optimize the performance. Okay, of the panels, and it should be in a local context. It is in the context of your country or the particular place where you are. What you can do. Especially, I will say to engineers and technologists, it offers a huge opportunity for looking at creative ways. Around the panel, you can do many creative things. Is that clear to everyone? Everybody understood?
Yes,
All
sir.
clear?
Yes, sir.
Okay. Okay. Now, with that, we come to the end of the solar photovoltaics. Okay. And what I'll do is I'll take the rest of the class, maybe about, 20, 25 minutes that we have. And I'll discuss another very important of these technologies, which is mentioned here, which is light emitting diodes. Now, there is a particular reason why I'm going to talk about light emitting diodes as a follow-on from the solar photovoltaics. Can anyone tell me what may be the reason?
So both use semiconductors.
Absolutely brilliant. Okay, very good. Uh, so that's the very interesting thing. Now, when you are doing solar photovoltaics, what are you actually doing?
We are using light to create holes in semiconductors, and
Brilliant.
we are doing
I
reverse.
mean, holes means you're using light to get energy, electricity,
Yes.
right? Uh, You're converting light into electricity. What are you doing in a light emitting diode?
The reverse of it.
Absolutely. You're just converting electricity into light. Okay. So, it's very interesting how more or less the same kind of a setup, but operated in a different way, gives you such profound technologies. Okay. Uh, so, so now we looked at it when we were talking about solar energy, and we talked about when you get forward bias, what did we say? That the depletion layer is progressively it vanishes. Why? Because this is the negative pole and it is repelling the electrons, so the electrons are moving into the bulk of the semiconductor, and over here likewise is the positive pole, and the holes are getting pushed into the bulk of the semiconductor, simply because is getting repelled by the positive pole, and therefore the depletion layer that existed in between, it kind of disappears. And for the depletion layer to disappear completely, you require something like a zero point 0.7 volt applied potential. Now, if you were to apply, okay, a potential in excess of that, what it means is that you are trying to push more holes, this way. Okay, the holes will keep moving this way, and your electrons will keep moving this way, right? Now, so when that happens, what will happen is that obviously the electrons and the holes will come in proximity. And if they are, how are they traveling? This, let's say, suppose I look at the valence band, and this is my conduction band in a semiconductor. And what am I really doing? When I'm applying more potential, I'm having a stream of electrons, uh, going this way. This was originally where my depletion layer was, okay? And this is what it may have to climb this hill before it comes to the other side. Okay? And likewise, my holes, will of course have an exactly inverted kind of an energy requirement, and so this is the holes will have to go this way to climb up the hill, and that's what will happen. This is what will happen. Now, when I've got electrons and holes in proximity, in other words, I can get a good Frank Condon overlap. Then obviously, what it means is that the electron and the hole will naturally recombine. Okay, when there is a vertical transition possible. Okay, so the electron will basically relax into the hole, and that whole energy, okay, of the excited state getting dissipated to ground state releases energy. Okay? Now, if that energy which is released is light, okay, then it is basically an optical light emitting diode. But light need not be the only pathway. In fact, the predominant pathway in most cases will be just heat dissipation. When these things combine, the electron and the hole. Okay, so the huge area of research is that how do I direct this particular process so that my relaxation of the from the excited state to the ground state actually is done through this kind of a light generation. And we already know that there are, for example, systems which are fluorescent. So everything does not relax necessarily by emitting heat. Okay, there are plenty of systems which are known which emit light. So it's a question of really understanding what are really the factors that lead to dissipation of energy thermally versus dissipation of energy optically. Okay? And that is the revolution which has happened in the area of light emitting diodes. Okay, is everybody clear of the principle? Is it all
Yes,
clear,
Yes,
everyone?
sir.
yes.
Okay. Okay. All right. So, and just to show you what a revolution it has been, and if we look at from the time of, let's say, General Electric, and Langmuir and the incandescent light bulb, okay, and you start looking, at what is the kind of power output which we could get. I mean, when we were kids, we had these those light bulbs. Of course, even today you have it, okay, and you had a 100-watt light bulb, and even with all the improvements made by Langmuir, you know that the amount of light that you get is very paltry, okay, from those kinds of light bulbs. Then, of course, came people realized it. What you had was the fluorescent lamp, and people realized that there are many parts of the of the wavelength, which are not actually being of the electromagnetic spectrum, which is not actually getting used for visible light. Like, for example, if I generate ultraviolet light, that I can't see it. Okay, so that's where the fluorescent tube became important, where people were able to convert then things like the ultraviolet radiation also into visible radiation, and that, of course, greatly improved the quality of light. And today, fluorescent tubes are still very popular. Okay? Uh, and then, the first light emitting diode was invented around 1970. It was a red LED, red light. Okay, and it later on became very popular. People started looking at some of these traffic signals. And so people started looking at red, yellow, and green. Okay, as the kinds of light emitting diodes. Now, what will control the color of this OLED? What will control the color of the light?
That band gap which will determine the.
Absolutely, the band gap. That's what it is. It'll be controlled by the band gap. So wavelength of emitting light is controlled by the band gap. Great. Okay, very nice. And now, just to show you, at what kind of a phenomenal speed, these developments took place. And by the way, in 2014, the Nobel Prize in Physics was given for the invention of the blue LED. It was given to a Japanese company, Nishia, and these are the people who actually got the Nobel Prize. Okay? Because what was very important was, what is the light that we all have in our house typically? What kind of light we use at home?
White light.
White light. Okay, we all, I mean, that is the light which is very common. And so in other words, we are going in the reverse of the direction in which Newton did his experiments with the prism, and split white light into the various colors. And here what you can do is that I can take a combination of different kinds of OLEDs, and which generate light of different wavelengths, and which when I combine, it becomes white light. And in fact, what was really preventing, this white light being generated was the absence of a blue LED. People could not find a blue LED. And that's what these Japanese people were able to do. They came up with a very efficient blue LED, and that is what made the entire thing of white LEDs commercialized. Okay? That's what led to it. Otherwise, it would not have been possible. Okay? So I hope you can understand that how important all of this is. Now, it's also very important to understand that in any of these innovations, further innovations will require quantification. I mean, you cannot say bright, very bright. These are all qualitative terms. Okay, so there has to be some kind of a definition of what is meant by efficiency of an OLED. So, can you quickly define it, one of you? How you would define the efficiency of an OLED?
The amount of light that it is generating per unit of power it consumes.
Absolutely. Okay, so it would be some kind of a light amount, in some appropriate unit. Okay, divided by what? Okay, so light intensity per watt. That's what it would be. Okay? So the standard protocol, is that you take a green laser. The reason why this is taken is, these are some of the laser wavelengths. Okay, so 540 into 10 to the power 12 hertz, is effectively used as the monochromatic radiation, and now that radiation has an intensity in a particular direction, in one direction, okay, of the intensity. You can always convert wavelength into watt, isn't it? Right? E is equal to, what is the E is equal to h nu, or I can say E is equal to hc upon lambda, right? So I can get the energy equivalent, isn't it, of a wavelength. Okay, so I get the energy, and for 540 into 10 to the power 12 hertz frequency, you can actually calculate that the energy is equivalent to 1 over 683 watt. Okay, and this is known as a this. Okay, is very important in a particular direction, and the units of light. One is the candela. Okay, and that's the one unit of light, and the other thing that you need to know is lumen. Okay, and this is the most common unit of light. Okay, a lumen is equal to 1 candela into 1 steradian. Okay, now what is a steradian? Just like, of course, in we have in a circle, we know the total angle is 360 degrees at the center. So if you take a sphere or a solid angle, okay, the solid angle is equal to 4 pi. Right? So effectively, if it is radiating in all directions, so effectively it's covering an angle of 4 pi. So let's look at the definitions. 1 candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 into 10 to the power 12 hertz, and that has a radiant intensity in that direction of 1 over 683 watt per steradian. Okay, and a lumen is basically one candela multiplied by, by the steradian. Okay, and so if I've got a solid angle, which has got 4 pi, okay, as the total angle, right? So I'll have basically one candela multiplied by 4 pi steradian. So that becomes equal to 12.57 lumens. Okay. So this is really, what is the kind of definition of light intensity, right, over a solid angle. Now, what people are aiming for is to try and maximize the lumens per watt. Okay. How many lumens can I get? So, for example, theoretical, as we discussed, you can have 683 lumens per watt. Okay. If you have white light, which will naturally require different wavelengths to be combined, the theoretical efficiency works out to be 350 lumens per watt. Okay. And about I think about 3-4 years back, Philips actually broke the barrier, and were able to generate OLEDs, light emitting diodes, with 200 lumens per watt. It's amazing. So they are already operating at something like about 60% efficiency. And but then you can also say that is it possible to go to 100% efficiency? Can I do that? So that's where the research will come in. That can I try to reach almost like a quantitative value in terms of light output. In other words, it's completely knocking off the thermal deactivation pathway, and all of the relaxation of the excited state basically emits light. Well, and by the way, just I'm not going to read this, but there are a whole host of different kinds of semiconductors, which have been developed, which where you can get name any light that you want, and today you can get it, with the OLED. Now, with that, we come to the close of the solar photovoltaics and OLED. And as you would have seen that these are two sides of the same coin. Okay. Any questions from anyone? Is it all clear? All clear?
Yes, sir.
Yes, sir.